First, let's get an idea about where things are happening and orient ourselves. So when we talk about metabolism, a lot of it's going to be happening in the mitochondria, and some of it's going to be happening in the cytoplasm. When we talk about glycolysis, that's happening in the cytoplasm. When we talk about the citric acid cycle, that's happening in the mitochondrial matrix. Most of it is just happening in the matrix, so this inner membrane, this inner kind of like chamber. But then there's also going to be the succinate dehydrogenase step, which is actually embedded in the inner mitochondrial membrane. And that complex is actually part of our electron transport chain. That's going to be complex 2 in the electron transport chain. And it's going to contain, that's going to be the step where we're actually generating the FADH2. That's one of the flavins. So the FADH2 is tightly held inside the protein complex. And so it's not soluble. It's got to be stuck in the membrane. And so we want it to be stuck in the membrane where we want it. So our succinate dehydrogenase is going to be in the membrane, in that inner membrane space. But the rest of things are going to be happening in the matrix. As I mentioned, however, glycolysis is happening in the cytoplasm. So when we're generating this pyruvate through glycolysis, that's going to be in the cytoplasm, and it needs a way to both get into the mitochondria and into the tricarboxylic acid pathway. In order to get into the tricarboxylic acid pathway, well, we need it to be 2 carbons. The whole idea of the tricarboxylic acid cycle is that we take this 2-carbon compound, acetyl-CoA, or the acetyl part of acetyl-CoA, and then we combine it with oxaloacetate. Oxaloacetate has 4 carbons. 2 carbons plus 4 carbons is 6 carbons. We join these together, we get the 6-carbon citrate. Then we lose 2 carbons in the form of CO2. So in 2 different steps, we're going to lose 1 carbon dioxide. We're going to lose another carbon dioxide. So we go from that 6-carbon compound back to a 4-carbon compound, which we regenerate to form this another oxaloacetate. And therefore, when we add another acetyl-CoA, we can continue on the cycle. Each turn of the cycle, we're getting 3 NADH, 1 FADH2, and 1 GTP. And this is, if we were doing this from glucose, we'd be doing this cycle 2 times because we'd have 2 acetyl-CoAs because we had 2 pyruvates. But how do we get from pyruvate to acetyl-CoA? In order to do that, what we have to do is we have to oxidatively decarboxylate it. If we look at pyruvate, it's what we call an alpha keto acid. So it has this carboxylic acid group, alpha to a carbonyl. So it's next to it, it's alpha. Just like when we talked about alpha amino acids, where they had like the amino group and the acid group right next to a carbonyl, that's the same sort of thing. We have an alpha keto acid. In this case, we have pyruvate. Alpha keto acids, if we want to decarboxylate them, that's going to be tricky. So we're going to have to go through some tricks, and we have to use these complex enzymes. These big complex enzymes we'll get into a little bit, but basically they're going to use the cofactor TPP, lipoate, FAD. They're going to take NAD plus because remember, we're doing oxidative decarboxylation. So not only are we decarboxylating this, but we're also going to be oxidizing this carbon. So normally when we think about oxidation, we're thinking about like, oh, you form a bond to an oxygen or something like that. Well, a bond to a sulfur is also going to be a form of oxidation because sulfur is going to be more electronegative than carbon. So if you were to break this bond, the electrons would get to go with the sulfur rather than with the carbon. So we say that carbon has been oxidized. And speaking of going with the sulfur and breaking the bonds, these bonds are going to be easier to break. When you have a bond to a sulfur, these bonds are easier to break than a bond to an oxygen. So if you make a sulfur linkage to something, that's going to make it so that you can kind of have a swappage point. And so this is what we're doing when we're forming this acetyl-CoA. Not only are we decarboxylating it, but we're also going to be kind of introducing a handle onto it. This handle is kind of like, it's going to make it easier to break this point. It's going to make it easier to attack this carbonyl carbon. and do things with it. It's going to be easier to attach this to another molecule. And it's also going to make it so we kind of have stored energy in this bond. In terms of what acetyl-CoA, what CoA actually is it's this kind of biggish molecule. When you see like CoA, it might sound like, oh, it's just a couple letters, it's probably this small little thing, but it's actually kind of this big bulky thing. It's derived from vitamin B5 or pantothenate. And you have basically the business end of it is going to be right here, where you have this sulfur that can form these thioester linkages. So in acetyl-CoA, this is our acetyl group, and it's on the CoA. Just a technical note that sometimes you'll see CoAs or like CoASH. Basically, that's just referring to the sulfur on the CoA. So it's part of the CoA. So it's not like there's an extra S on it. It's just emphasizing that there is that sulfur that's going to form those important reactive links that's going to allow you to make these thioester linkages. And these linkages, remember, are kind of like our handoff points, our swappage points. So by putting an acetyl-CoA on something, or by putting a CoA on something, we're able to have this point where we can swap things out, this point where we're able to make carbon-carbon bonds, because making carbon-carbon bonds is often pretty tricky. But by putting by putting a CoA group on it, well, now we have a way to do that. And remember, though, that this acetyl-CoA group, this CoA group is going to be kind of big and bulky. We're not going to want to transport it through the mitochondrial membrane. Instead, what we're going to want to do is we're going to add it once we're already in the mitochondrial matrix. So our acetyl-CoA is going to be added, is going to be formed in the matrix. We're going to make that pyruvate in the cytoplasm. Then we're going to take that pyruvate into the mitochondrial matrix, and there we're going to carry out our oxidative decarboxylation. This oxidative decarboxylation, it removes a carbon dioxide, it gives us an NADH, which we can later cache in, and it's going to give us our acetyl-CoA. Let's get back to the idea of kind of like, well, what's actually going on in this cycle? First off, the name. So the citric acid cycle, well, that makes sense because we've got citrate. So remember, citrate, that's going to be the 6-carbon compound that we form when we join an the acetyl group from acetyl-CoA to oxaloacetate. When we're doing this, we're releasing the CoA. And remember that CoA, we had that reactive thioester group that's going to make it so that this is easy to break and form a bond to carbon. And so that's what we're going to do. We're combining these to form our citrate. This is a tricarboxylic acid. So we've got these 3 carbon dioxide groups, 1, 2, and 3. We're going to lose this one, and we're going to lose this one. And both of these are actually going to be coming from the oxaloacetate and not from the acetyl-CoA. So as we'll discuss, to actually get rid of the carbons from this acetyl-CoA, we're going to have to go through 2 more cycles. But let's get back to our story, where we're starting this pathway. We have this citrate formation. This is going to take place with the help of an enzyme called citrate synthase, which is going to be one of our regulated steps. When we do this step, as you might expect, since we're breaking off that CoA, we're going to be getting this is going to have a nice negative delta G. This is going to be energetically favorable, and we're also going to want to regulate it tightly. But when we join those together, we get our citrate, we get our 6-carbon molecule. Now we're going to take an enzyme called aconitase. And aconitase, what it's going to do is it's kind of just going to switch the position of this OH group, this alcohol group. So remember that we have this carbon dioxide here, and we have this carbon dioxide here. We want to basically get this into a form where it's going to be easy to lose a carbon dioxide. And we talked before about how if we had an alpha keto acid, that was going to be hard to get rid of. And we'd have to go through one of those complexes where we used all those complicated tricks like our pyruvate dehydrogenase reaction. We had this big multi-subunit complex where we had all these cofactors. And I'm not going to go into the mechanism, but basically you're swapping off, you're getting rid of the pyruvate is going to then get attached to this enzyme, and then that's going to get passed off from place to place within this enzyme, ultimately generating NADH and our acetyl-CoA. We can go through a similar situation to do the oxidative decarboxylation of other alpha keto acids. But if we can change something out of being an alpha keto acid to being a beta keto acid, that would be favorable for reasons we'll get into in a second. If we look at citrate and we look at isocitrate, what we have here is we have this OH group on the central carbon, and here we have the OH group right here. If what we do is we were to oxidize this hydroxyl group, what we would end up with is that we would have a beta keto acid. It would be alpha beta to this carboxylic acid, and then that would be easier to lose. Let me show you a little more explicitly what I mean. So with our isocitrate, we had set things up so that we had this oxygen here. When we have this oxygen here, basically what we've done is we've went from the case where we went from having basically this tertiary alcohol, which is going to be harder to oxidize, to having this secondary alcohol, which is going to be easier to oxidize. When we oxidize it, now we end up with having this beta keto acid. And as I mentioned, beta keto decarboxylation of a beta keto acid is favorable. Why is this? Well, if we think about what happens to happen in order to decarboxylate, remember that our carbon dioxide is CO2. If we have these oxygens flow back onto to form a double bond with this carbon, that kicks these electrons off. These electrons then get pushed onto forming a double bond with this carbon, which forms an enol, or an enolate in this case, because we don't have a hydrogen right here. But basically we have this enol group, and we get that enol keto tautomerization, that same thing that we saw in the case of our phosphoenol pyruvate going to pyruvate. We saw that was going to be really, really favorable because we got that enol keto tautomerization. Remember that the oxygen would much rather have electrons than the carbon. So if you're able to go from an enol form to a keto form, that transition is going to be energetically favorable. In the case of our this decarboxylation, what we're doing is we're taking this, and we're forming this enol, or this enolate, and then we're going to unform it. So we're going to basically go back to the keto form to give us alpha ketoglutarate. Having that transition, that enol keto tautomerization, is then going to make this very energetically favorable. And so in the enzyme active site, it's able to help coordinate things, make it so that you have this manganese that's going to be helping all this out, and you're going to get this highly favorable interaction where you get this oxidative decarboxylation. And going back to how we set the scene for this, first we took our citrate and we made our isocitrate. What we did here was we were changing the position of this alcohol group. By doing this, we went from a tertiary alcohol, which would be hard to oxidize, to a secondary alcohol, which would be easier to oxidize. Additionally, this set us up so that when we did oxidize it, we would end up with a beta keto acid, because we would have this carboxylic acid group be alpha beta to a ketone. Now what we could do is we would do that oxidation and we would do that decarboxylation. And that was all happening by this isocitrate dehydrogenase. So that was happening in between our isocitrate and our alpha ketoglutarate. We don't see that intermediate we just talked about, this oxaloacetate, because it's going to be highly unstable. And so we're not actually going to see that in our tricarboxylic acid pathway, but it is an important part of this mechanism. So what's going to happen next is we want to get rid of another CO2 group. So we got rid of the CO2 group, which was coming from our original oxaloacetate. Now we're going to get rid of the second CO2 group, which was also coming from our oxaloacetate. We'll get into this in a minute, but basically at this point, the enzymes that are responsible can tell that the ones at the top, that these two came from our acetyl-CoA, and that these ones came from our oxaloacetate. Basically, when you have the citrate synthase reaction, this is kind of held in the enzyme active site so that it can only attack from one face, and therefore the enzyme knows, like, yeah, those ones on the top, they came from the acetyl-CoA, and the ones on the bottom, they came from oxaloacetate. So if you say had a tracer on one of these carbons, you'd be able to tell them apart, and you'd be able to tell that it's going to be the second cycle when you're actually going to start losing them. So what's going to happen next, though? We need to actually lose that second carbon dioxide. And if we look now, well, now we have another alpha keto acid. And if we have an alpha keto acid, we can't do that simple keto tautomerization trick we used before. Instead, we have to go back to resorting to those complicated gymnastics that we used in the case of our pyruvate dehydrogenase complex. You can do there are similar enzymes that will do this oxidative decarboxylation of various sorts of alpha keto acids. We'll see that we can do things like break down branched chain amino acids. These alpha keto acids of that, we can break down using a similar mechanism, using a branched chain alpha keto acid dehydrogenase complex. Basically, it's going to be another one of those big complicated things. And here you can see that we have this E1, E2, and E3, which is actually very similar to what we had in the case of our pyruvate dehydrogenase complex, where we had our E1, our E2, and our E3. E1 is the only one that's actually, this is the one that actually binds to the substrate. E2 and E3, these are kind of just where they're passing things around and doing the reduction reactions, the oxidation reduction reactions. And it turns out that E2 and E3 can actually be shared between different complexes, whereas the E1 will be specific for your substrate. E2 and E3 can actually be used for the same sorts of things. And so we see the same machinery kind of reused in different forms. So we can take this alpha ketoglutarate and make succinyl-CoA, or you take pyruvate dehydrogenase and make acetyl-CoA. These are going to use very similar mechanisms. We're using that TPP-dependent enzyme. It had that like lipoic acid. It had used NADH. It used CoA. We give it a CO2, the same sorts of gymnastics. Really cool stuff, but I don't have time to get into it. But that is going to be how we're going to do that second decarboxylation. And so again, we're going to be generating an NADH. And we've attached another CoA back on. So now we have succinyl-CoA. So we had CoA kind of come and attack where this carbonyl carbon is and push off this CO2. So we've lost this CO2, and this is an oxidation because remember that we have a sulfur group that's adding to this carbon. Sulfur is more electronegative than carbon. And so this is going to be an oxidation reaction. We have this reactive thioester that's going to make it easy to break off this CoA and then use the energy from that hydrolysis in order to drive something. In this case, what we're going to be driving is the formation of our GTP. So before we use that energy in order to basically make a carbon-carbon bond, now we're going to be using that energy to make GTP by adding an inorganic phosphate to GDP to give us GTP. When we do this, now we've lost that CoA and formed succinate. So this is going to be our succinate, and the step was carried out by succinyl-CoA synthetase. Note that for this step, sometimes you'll see like ADP and ATP. There are different enzymes that are used in different levels in different tissues and different organisms that may make ATP or may make GTP. But when we make GTP, it can be easily interconverted to ATP. Basically, there are very similar energetic-wise, and so it's not energetically costly, really. You can basically interconvert the different NTPs fairly simply. Now what we're going to do is basically we need to regenerate our oxaloacetate. In order to do this, we're going to do another oxidation step. So this succinate dehydrogenase step, remember, this is the step that's actually going to be happening in our inner mitochondrial membrane. This is going to be our complex 2. We want it happening in the membrane because the FAD is going to be one of those flavins that's going to be tightly embedded in a protein. So we need that protein to be embedded in the membrane in the place that we want it. By having this reaction here, well, we've got it where we want it. We're generating this FADH2. We need to regenerate the oxaloacetate if we want to redo this cycle. So what we're going to do is we're going to oxidize it. We're going to form this double bond here. Then we're going to oxidize it. We're going to hydrate it. add this OH group, and we're going to oxidize the OH group we just added in order to form a carbonyl, giving us our oxaloacetate. Notice that in this step, we're generating NADH, and in this step, we're generating FADH2. Thinking back to why this might be, well, if we're going from a carbon-carbon single bond to a carbon-carbon double bond, that's going to be harder than going from an alcohol to a ketone. We're going to need a bigger difference in our standard reduction, in our reduction potentials. FAD has a higher reduction potential than NAD+. Basically, what this means is that it's going to want the electrons more than the NAD, and so we're going to get more energy if we give those electrons to FAD than if we were to give them to NAD+. The energy that we get is going to be enough to form this double bond, but it's also going to make it so that we don't have as much energy left over when we go to cache those electrons in for our ATP generation. But in the case of why it is, it's because we have lower energy left over because we had this bigger difference in our standard free energies when we reduced the FAD. That was giving us enough energy to do this double bond formation, but it left us less left over, so we can't use as much to make ATP. But what we've done is we've oxidized this to fumarate, we've hydrated it to malate, then we've reoxidized it to oxaloacetate. So these steps are kind of setting things up to reform our oxaloacetate, and now we can do this cycle yet again. Going back to our idea of when do you lose what? So in the first turn of the cycle, we're going to be losing this carbon dioxide, this CO2, and the second cycle, we're going to be losing this CO2. Both of those CO2s were coming from our oxaloacetate. So the enzyme that makes the citrate synthase, the one that joins acetyl-CoA and oxaloacetate to give us citrate, it can actually tell these apart. It's kind of sitting in the enzyme's active site in a way that you only get this attack from one face. And so you get this stereochemistry such that the carbons that came from our acetyl-CoA are going to be different than the carbons, or you're going to be recognized as being different than the carbons that were dealt with from the oxaloacetate. And it's this side, these carbon dioxides, that we're going to lose. At this point, so if we were tracing these, we would have that our labels, if we had this like radioactively labeled, our labels would still be up here. They would not be lost in the first step, and they would not be lost in the second step. They wouldn't be lost until the second cycle. And to lose both of them, you'd actually kind of have to on net go through two more cycles. Why is this? Well, basically, what happens is that although at the first step it could tell things apart, once you get to the succinate step, here this is going to be symmetrical. The molecules can't tell apart, so these carbons are kind of mixed together. If these carbons are mixed together, what this means is that, well, on the next cycle, you're only going to lose half of the four that were here, and if they were all scrambled up, well, now what's going to happen is you're going to lose one that was from, on average, you'll lose one that was from the cycle before and one that was from the cycle 2 before. So in order to actually get rid of both of those carbons that you brought in, you would have to go through the cycle 3 times. So if you've heard that you have to go through the cycle 3 times per acetyl-CoA in order to get rid of both of those carbons, that's what it's talking about. And then remember that you have 2 acetyl-CoAs per glucose molecule because you had 2 pyruvates per glucose molecule. So you get 2 acetyl-CoAs. We can keep doing this cycle as long as we keep feeding in acetyl-CoA. And we don't take these other things away.